close the door. So if you can't see the board, let me know. So what we're looking at, we're going to finish up chapter 2 today, 2.6, and then we should be able to finish 3.1, at least I hope we can. Although the kerfluffle that kerfluffle, I think that's the word, that happened last week is I thought I skipped a subject. I thought I'd skipped one-sided continuity, and I was like, oh no. And then I went back and said, okay, no, we covered it. I looked at the video and looked at my notes. It's like, okay. And I think what had happened is I went over one of the videos and I saw one-sided limits, but I didn't see, I mistaken that for the continuity part. So I apologize for any confusion that might have been there. But I had a little bit of a panic, like, oh my gosh, I didn't teach this, but it's there. It is there, and so you do have one-sided continuity. And it's an interesting idea. Basically, you have 3 continuity tests. You have the continuity of a point that's sort of in the middle here. So you have A, B, oh, let's call this C, call this B. And so when we talk about continuous, we typically mean something like point C here, or x equals C. And so you can approach from either side. You're going to have a double-sided limit available for your continuity test. But then you have right-sided continuity. And I know this sounds kind of strange, but that's when you're approaching from the right side with your limit. You only have one limit available to you because there's no domain over here. So you have right-side continuity, and then for your limit here, you only have a left-sided limit available to you. So you get left-sided continuity. Well, we're going to get something similar with derivatives. If we get that far, it's really in 3.2. We might not get there. But there is a similar idea, and that's what chapter 3 is going to be. We're going to get into derivatives, more calculus. So we're getting into infinite limits. This is the last part of 2.6. Now, we looked at last time what happens if x just becomes bigger and bigger and bigger in the positive direction, or if it keeps going farther and farther in the negative direction. We call those limits as x goes to positive infinity or negative infinity. What we're looking at here, though, is different. Here we're going to be looking at situations where x is going to be approaching, a number, some kind of number, x equals c. Excuse me, but the function grows bigger and bigger and bigger. And that can happen too as x goes to infinity or negative infinity. Think of the line y equals x. It will, well, you'll see. But if you take the limit as x goes to infinity, this will turn out to also be infinity. We're going to talk about this a little bit more. In other words, the function f of x here just gets bigger and bigger and bigger as x gets bigger and bigger and bigger. But let's take a look at the definitions here, what's going on. So first off, the limit as x approaches some number c of f of x equals infinity. So here, x isn't growing bigger and bigger. It's just getting close to some number c. Now, what kind of situation is this? Well, you could think of something like 1 over x. If you have 1 over x and you approach 0, say, from the right side. So in this case, you'd be approaching 0 plus. As you get closer and closer to the right side, so 0 plus, f of x is just going to grow bigger and bigger and bigger. Again, that means approaching from the right side of 0. We're going to say this is equal to infinity. So, not practically speaking, in terms of formal definitions, what's going on? So, in terms of just the nitty-gritty, as they say, the details, this is true if for every positive real number B. So it doesn't matter how big B is. You can think that B is standing for big. So for every positive real number B, there's a corresponding delta greater than 0, such that if the distance between x and c, so x is getting closer to c, as it gets close, so close to c, the distance between x and c is less than delta, then f of x is bigger than that monster B number. So the closer x gets to c, like if this delta gets smaller and smaller, this distance needs to be getting smaller and smaller. So the closest you're getting to c, this is getting bigger and bigger. Because B, you can make this any big number you want. You'll just find a delta that's small enough to make everything work out. So that's the idea of going to positive infinity. So what about negative infinity? So what we have here, again, let's take a look at this. Now, in this case, if we approach, move along the x-axis towards 0 from the negative side, or the left side, f of x is just going to get farther and farther down. So here the limit, as x approaches 0 negative, of 1 over x, that's going to be negative infinity. So you approach from this side, f of x just drops and drops and drops. So that's the idea of having this negative infinity for a limit. So again, the formal definition. Take a look at that. So this is true if for every real number negative b. So this is going to be, and make this in point, this is negative. Now this might seem like a silly detail here, but negative b, we're going to assume b itself is positive, so negative b becomes a negative number. So for b itself, make this a note. B itself is greater than 0, so negative b is going to be less than 0, or a negative number. There exists a corresponding delta greater than 0, such that And again, as x is close to c. So again, absolute values we can think of as distance. So the distance between x and c, it's going to be small. Then f of x is less than this negative b. So again, b is this huge number. It's a big number. And so negative b is going to be a negative number way down the x-axis on the negative side, just way down there. So these are the formal definitions for this sort of thing. And let me go through an example. Again, it's not something you're going to see really in your homeworks, but just to show you how this works. At least the homework that's showing in the textbook. So I'll go through this. So we want to prove this is true. And to do that, we're going to start out with this idea. We want to show something like this. And we're going to look for a delta that's going to allow this to happen. So for any number we get here, we can find a corresponding delta. So that being the case, f of x is this. And b could be a million, a billion, a trillion, something. So we can make this observation that because negative b is negative, it's going to be less than 0. And if we multiply through by -1, I'll make a little note about that. What we do here is we just multiply everything by -1. So that's how we get this. And when you multiply through by a negative, it switches all the inequalities around. So we'll focus in on this. Now what we're going to do is take reciprocals. And if we do that, what we're going to get is, again, our inequality is going to flip. So we get something like this. So next what we can do, we're going to actually try to solve for x minus 3. And the reason we're going to try to do this, we're going to look for that distance, that x minus c. And again, this takes some practice to see something like this. But if we square root this, because this is squared, we're going to get an absolute value. So that'll give us, and since our c is equal to 3, we're going to get an absolute value of x minus 3, which is, that's going to kind of tell us about our delta. So multiply both sides by 2. Square root both sides. And so what we're going to get is this can be our delta. So for our answer, and there we go. So whatever negative b we pick, and again, b is some big number, we're just going to make it negative. The delta is going to be square root of 2 divided by that b, however big it is. And then we're going to see this. The distance between x and 3, when it's less than delta, you're going to have an f of x that's going to be less than negative b. Again, whatever number you chose for negative b. So a positive number. So that's how you use the formal definition. And again, I don't think that's, at least in the textbook, it's not in the homework there. So I can double check to see if it's going to be showing up in the computer work. But then if it does, you have at least some example to follow. And if there is something that I can check to make sure. But the main emphasis in this chapter or this section is just doing this with your hands, by hand. So not so much the formal definitions. So let's take a look at something. We talked about horizontal asymptotes last time. So vertical asymptotes. So what we looked at in algebra is, again, a great example of this. Our function f of x is 1 over x. So let's see if this works. So here's our 1 over x. And we have a vertical asymptote at x equals 0. Now, to recall what a vertical asymptote is, a vertical asymptote is going to be a vertical line that our function cannot cross. Now, horizontal asymptotes, the function can cross that. Those are okay. Oblique asymptotes, functions can cross those. But vertical asymptotes, no way. Those are off limits. So with the vertical, it's usually where you get something like a division by 0. It's a very commonplace thing to give a vertical asymptote. So the way we can identify these with calculus is we can use limits. And this is what we use. So here are two conditions with limits. So in this case, as you approach x equals a, you're going to get a limit for your function that's positive infinity or negative infinity. So if we're approaching from, say x equals 0 from the right side, in this case, you're going to get a limit of positive infinity. The other criterion as you approach from the left, you're also going to get an infinite limit. And so in this case, as we approach 0 from the left, we get a limit of negative infinity. So that's one way of expressing these using calculus. So let me do an example. We'll look for some asymptotes. So in this example, here, I'll put some notes here before we jump in. For this one, the limit as x approaches 0 from the right of 1 over x, that's going to be infinity. And then the limit as x approaches 0 from the left, this will be negative infinity. And so the vertical asymptote will be x 0. And we'll do another example like this. Now, one thing that helps with these kinds of problems, it does help to graph the function, see what it's doing. So this is where like graphing software or graphing calculator, something like that could be really helpful. So for example, say we're going to find the vertical asymptote and the horizontal asymptote for this. Y equals x plus 3 over x plus 2. Now let's go with horizontal asymptote first, because we've worked with the limits as x goes to positive infinity or negative infinity already. So for the horizontal asymptote, well, the way we do this, we take the limit, and let's go as x reaches out to positive infinity. So what we're looking for is, how does this function behave as x gets bigger and bigger and it heads down the positive side of the x-axis? So we can divide everything by x. A little trick here for getting this limit. So all 4 of these terms are going to divide by x. Or another way of putting it, we divided the entire top and the entire bottom by x. Now, if we let x go to infinity, this will come out to 1 plus 0, 1 plus 0, 1 over 1, all 1. And so that's the limit as x goes to infinity. So that's half of it. Now we got to find what happens to this function as x goes to negative infinity. So it's going to be the same approach. And again, we're going to divide everything by x. So this is going to be, of course, familiar. And what we're going to get is 1 plus 0, 1 plus 0, 1 over 1. And again, we're going to get 1. So for finding the horizontal asymptote, because the limit as x goes to positive infinity and as x goes to negative infinity are the same, the horizontal asymptote is equal to y equals 1. So that gives us the horizontal asymptote. And the way we come up with that is we let x go to positive infinity, we see what the function does, and then we let x go to negative infinity, and we see what the function does. Now we take a look at the vertical asymptote. Now for this one, there's ways you could do this analytically, but what I'm going to do is I'm going to take a shortcut. I'm just going to draw a picture. So first off, we'll note that the denominator is x plus 2. So let's set this equal to 0. And so what we're going to get is really a good candidate vertical asymptote at x equals negative 2. Now if we graph this, so we have a horizontal asymptote at y equals 1. And we're actually going to get a vertical one at x equals negative 2. Now we're going to show this is the case using our limits. But if you graph this function, this is what's going to look like. So with this picture, let's compute the limit as x approaches negative 2. So the limit as x approaches negative 2 from the right. Well, if we look at this graph, if we approach negative 2 from the right, the function's rising up. It's going to climb up this vertical asymptote. So this is going to come out to be positive infinity. And then we take a look at the limit approaching negative 2 from the left. And again, I've been calling this a vertical asymptote. From algebra, that's what we've been doing. But to put this in the language of calculus, as we approach from the left, our function, once we get close to negative 2, it's going to drop down. I get negative infinity. So using calculus, we've shown that the vertical asymptote is equal to x minus 2. This line satisfies the criterion using limits that that is in fact the vertical asymptote. There we go. Questions about that? All right. So I do want to mention something real quick. We're going to revisit an example we looked at last time with the oblique asymptote. And it was a function like this. So I skipped over this last time, but we've got time to do it. So I'll go through the division here. So you have 2x minus 4. We're going to divide this using long division. X squared. And we need an x term, so we're going to put in a plus 0x minus 3. So the first thing we're going to do, first term divides in the first term. It'll go in half x times. So we could say x squared divided by 2x, 1/2 x. So yeah, 1/2 x. Then we take 1/2 x times this whole thing. And we'll get x squared minus 2x. You got to be careful with the subtraction here. X squared minus x squared is going to be 0. But 0 minus a negative, it's going to be a double negative. So it's going to become plus 0 plus 2x. So we just get 2x. Bring down the -3. And we're through our first cycle of division. So we got one more cycle. This time we'll divide 2x into 2x. So +1. Then 1 times 2x minus 4. 2x minus 4. We'll subtract. 2x minus 2x is 0. -3, subtract a negative. It's going to be double negative again. So -3 plus 4 is 1. So that means our answer, 1/2 x plus 1 plus 1 over 2x minus 4. And so that's what we had last time. And so the thing to look at here, we're going to talk about something called dominant terms. And the idea here is that as x gets bigger and bigger and bigger, you're going to find that the remainder we have here is going to lose influence on f of x. So again, all we've done is we've changed the appearance of f of x. So this is the same as this, just a different way of looking at it. So what we're going to do is, let's take a look at this as x either heads down the positive x-axis towards infinity, or goes down the negative x-axis towards negative infinity. So I'm going to rewrite this. And if you don't recall from algebra, when we have a remainder of 1, we can express that remainder as well. We could say 1/2 x plus 1, remainder 1. Or we can add the remainder to our result and then put the divisor underneath that remainder. So what happens to this, let's say, is x goes to infinity. So again, we can divide by x everywhere, the largest power of x. And as x goes to infinity, we're going to get 0 over 2 minus 0, 0 over 2 over 0. So as x goes to infinity, then 2x minus 4 goes to 0. So this remainder term, I mean, it's a complicated term. 1/2 x plus 1, that's just a line. That's not too bad. We can handle lines. But this can be a little tricky. But as x gets bigger and bigger, this thing's going to go away. Now let's take a look at x going to negative infinity. And we're going to do the same thing. Like we're dealing with limits as x goes to infinity or negative infinity. We're going to try dividing by the largest power of x. So we'll get 0 over 2 minus 0, same thing. Then I get 0. So in sum, as x goes to negative infinity, and 1 over 2x minus 4 goes to 0. So what does this actually say? Well, as x gets, if we take the absolute value of x, say, as the absolute value of x gets large, then what's going to happen is that 1/2 x plus 1 plus 2x minus 4, well, this last term is going to go to 0. Now, it's not going to be exactly 0. Where we have these arrows, it's going to 0. So this will approximately be 1/2 x plus 1. And again, this is the case when x, whether it's a big positive number or a negative number that's way down the negative axis, when the absolute value of that gets really large. So what we say here is that these terms dominate as x goes to infinity or x goes to negative. Questions about that? And again, this is a rehash of the example we saw last time. I just wanted to go through it. One thing, we can go through the division of polynomials in calculus. Anytime we can do a little review of algebra, we can sneak some in there. It's not a bad idea, because it really can be a review of calculus. I'm sorry, algebra. The other thing is this idea of dominating. I just want to emphasize that. This notion of dominating terms. This can come up to some extent in a field called, or a topic of calculus called Taylor series. It's a very powerful idea. You can use it to approximate certain functions when they're very close to a point. And you can do some neat stuff with that. And that comes up in a lot of like theoretical physics and mathematics. You'll see those. And some applied stuff too. All right. So now I'm going to go back to these limits that go to infinity. I want to show you an example where we can use an analytical approach to kind of see what's going on. And then you can always check it with a graph. So let's say we have this. And we can bring this up. We can expand on this. This is a difference of squares. So we can say this is x minus 2, x plus 2. And then x minus 3. So we can see some problems here. If we take a look as, and we're going to focus on one limit. We're going to focus on this. And let's see, because we have two to choose from. Let's say we're going to look at x equals 2. So for x equals 2, we've got a problem. We're going to get a division by 0. And we'll get the same for negative 2, but just for the example, we're going to skip it for now. So this is going to be problematic. Now let's explore the limit. And again, we're going to do this analytically, but I really recommend, if you can, check it using the graph. Let's take the limit as x approaches 2 from the right. Now, if we do this, there's some advantages we have here. Like if we try to look at the limit as x approaches 2, I mean, we're sort of, we're going to see a division by 0. And that's going to kind of make it hard. We can't, there's a little more, let's say, detailed approach with using these one-sided limits. And this is what we're going to get. So what happens as we approach 2 from the right? Well, this is going to be, say, numbers like 2.1, 2.05, numbers like that. Well, they're still smaller than 3. So 2.1, 2.05, you have those numbers subtract 3. This is going to become, it's going to become 0. Oh, not 0, I'm sorry, it's going to become a negative number. Now, again, 2.05 and 2.1, what's going to happen here? Well, this is going to become, well, positive. We're just taking a positive number and adding it to 2. So as we get closer to the 2, I'm going to say it becomes positive, but really it remains positive. Now, what's happening here? As we approach 2 from the right, it's going to be positive, but it's positive becoming 0. So what's happening here? Well, before we never get to 2, but basically what we're going to have is a division by 0. It's going to imply infinity. So we know that much. But which infinity are we talking about? Like, I'm saying infinity here, but I'm going to be kind of general. So maybe I should be a little careful. Not sure if it's plus or negative. But as we deal with numbers just above 2, what that's actually saying is we're going to have a negative, positive, times a positive, and this equals a negative. So what this is implying, which infinity are we talking about? Implies negative infinity. So we want to kind of imagine, like, instead of 2, we could say 2.05 or 2.1. And what's 2.1 minus 3? 2.1 minus 2, 2.1 plus 2, positive, positive, negative. So all the numbers here we're going to be dealing with, they're going to be negative numbers, and as you get closer to a division by 0, well, this whole thing's going to grow, but with a negative sign attached. So we're dealing with negative infinity. Now let's take a look if we approach from the left. So now we're dealing with numbers that are smaller than 2. So imagine 1.9. So 1.9 minus 2, this is becoming negative. Let's call it negative. Now 1.9 plus 2, that's going to be positive. But then 1.9 minus 3, that's going to be negative again. So what's going on here? Well, again, as x gets closer to 2, we're looking at a division by 0. We're applying a plus or minus infinity here. Now, which one are we dealing with? Well, if we take a look at this, we have a negative over a negative times a positive. That's going to be, oh, sorry, no, positive. Oh, red, yeah. So we're going to be looking at a positive number. So this is going to imply positive infinity. So one thing I'm going to recommend, though, with this problem, I'm going to recommend graphing. And if we graph it, in that sense, we can remove all doubt. So if we graph this thing, what we're going to see kind of a lopsided shape. And again, we're only looking at what's happening here. If we double check what's going on, what we're going to see is the limit as x approaches 2 plus of f of x. In this case, it is going to be negative infinity. And then limit as x approaches 2 from the left over here, it's rising up. We're going to get positive infinity. So questions about that? So again, if you graph this thing, that's probably the safest thing to do when working with these kinds of questions. You can try to get some analytical insight. A good graph will that'll help you see what's going on. So questions about that? So that's it for chapter 2. So as far as the exam goes, that's as far as we're going to go. Let's see. So we're getting into chapter 3, and this is one of the topics of calculus, sort of the mainstays. Limits are always going to be there with us. We're always going to be doing limits in the background. But as far as one of the tools we're going to be working with directly for the rest of the course, that's what we're picking up in chapter 3, derivatives. So we're going to look at a definition. This is a rehash of what we looked at in section 2.1. We've seen this kind of thing already. We call it the difference quotient, and we're going to use this to develop well, we've seen it in action, but we're going to hang on to this tool and develop it more throughout this chapter. The difference quotient turns out to be something very significant. So the slope of a curve at x0, f of x0, is the slope of the line tangent to the curve at x0, f of x0. So the slope of a curve at x0, f of x0 is the slope of the line tangent to this curve at that same point. So what this looks like So we're talking about the slope of this line. So it's been a while since we talked about it, but a tangent line contacts a curve at only one point, while a secant line will cut through a curve at 2 points. And so what we're going to do is this. We're going to create a tangent, starting out with the secant. And so we're going to kind of do this in stages. So we're going to have 2 points, x and x plus h. And what we're going to get is x plus h equals f of x. What we're going to do is move this point closer to this point, and by doing that, h is going to have to shrink. Let me go back here. I'm going to put a little 0 here. So in your notes, I'm going to put a 0 on the x. We're working with a specific value of x. So we're going to keep that here at 0. So what's happening here? This line as we move this point closer, we're going to get something that more resembles a tangent line until finally arrows here pointing at the f of x value. Right in this gap, we have h. So what's happening here as basically as h goes to 0, then x0 plus h, f of x0 plus h goes to x0, f of x0. So these 2 points are basically going to become the same point. Now, to describe the slope of this secant line, we calculate the slope using the slope formula. So we could say something like, call this x1, y1, x2, y2. And then the slope of the secant line well, it's our slope formula. Y2 minus y1, x2 minus x1. And so plugging this in, what we're going to get is f of x0 plus h minus f of x0 over x0 plus h minus x0. And simplifying down, we'll get some x0s that cancel out in the denominator. Over h. So that's how we're going to find the slope of the secant line. So how do we find the slope of the tangent? Well, what we did is we said in section 2.1 that h will become practically 0. Now, because it's not actually 0, we can do some divisions by h, cancel h's in certain places. And because it's not actually 0, we don't have to worry about dividing by 0. But then once we've done our cancellations, we'll sort of go back to that idea of dominating terms. There are going to be some terms that will dominate because they don't have any h's attached to them. And the h's themselves, they're going to 0. And terms multiplied to those h's, those might go to 0 because they're not going to be dominating terms. So that's how we came up with our slope for the tangent. We're going to basically let h practically be 0. And so for the tangent slope, need some more space here, but it's going to be the limit as h goes to 0. So we're going to let h be practically 0. F of x0 plus h minus f of x0 over h. And we have a special notation for this. You're going to see this for the rest of your calculus career. F prime of x0 So there are 3 main tools that we use in calculus. These are new to us. These are the limit, where a number is practically a number. It's not exactly equal. So that helps us get around divisions by 0 and stuff like that, where those would usually become undefined. The other tool we're going to use is the integral. We'll get to that later. But the other one, aside from those, is this. It's called the derivative. So this is the derivative of f of x at x equals x0. Another phrase you'll hear, we also refer to this as the instantaneous rate of change of f of x at x equals x0. So any questions about this? We're going to do a couple examples, and then that'll pretty much cover 3.1. But this is a powerful idea, the ideas of rates of changes of functions. Why is calculus so interested in this? Well, a lot of things in nature, when you record data, you're recording rates of change. And if you can learn something about the rates of change, you can then ultimately use, well, various techniques and mathematics to determine, well, what is the function that has these rates of change? And it can get pretty complicated. And a good, powerful subject, very foundational subject for engineering, say, and physics, differential equations, where you have equations that contain derivatives. And you try to figure out, okay, if the rate of change in this function has this kind of relationship, if it works a certain way in an equation, can we figure out what the original function was? And it's a very powerful idea in engineering and in physics, or really a lot of different things. So you'll see more of this. Well, we're going to see a lot of it in this class. So that's the idea of this instantaneous rate of change. So let's take a look at an example here. So find f prime of a for f of x equals 1 over x. Now in this case, what we're doing is we're letting x0, I'm going to call it a. Now in all seriousness, we could have just let this as x0, but all right, fine, we'll do it this way. So what we're going to do, we're going to take a look at our difference quotient. So the limit as h goes to 0 of f of x0 plus h minus f of x0 over h. So in this case, x0 is equal to a. So you have the limit as h goes to 0 of f of a plus h minus f of a over h. So we know what f is. F is 1 over x. So in this case, this will be our x, and this will be our x. So the limit as h goes to 0, 1 over a plus h minus 1 over a divided by h. So what we're going to do, we've got a complex fraction here. So what we can simplify, let's make this fraction a little less complex. So let's try to cancel some denominators. So to do that, I'm going to multiply through by this denominator times that denominator. And same thing here. What we do to the top, we've got to do to the bottom. As far as multiplication and division go, what we do to the bottom, what we multiply and divide, but the multiply and divide by in the top. So we'll distribute through. Here, I'll get a stronger pen. So a plus h is a. We're going to distribute this to here. We'll distribute it both terms. So minus 1 over a. And again, a plus h times a. All right. So we want to look for some cancellations here. And this technique is going to let us do that. We can cancel this. And we can cancel that. So hopefully this makes life easier. Limit. And as h goes to 0, this will be 1 times a minus 1 times a plus h. Okay, so far so good. And then in here, we can distribute the h and the a to here. We'll get h a squared plus h squared a. So what's going to happen on top? A minus, well, 1 times a plus h is a plus h. We're going to distribute this minus through here. We're going to get that. And fair enough. Now, a minus a is going to be 0, so we get negative h over ha squared plus h squared a. So the danger here is if we let h go to 0, we're ultimately headed towards a division by 0. But what we can do is factor out an h. If we could get one term in the denominator to not be h, we're going to be in good shape. And so what will happen? Those will cancel. Limit. As h just goes to 0, we get negative 1 over a squared plus ha. And at this point, we can think about those dominating terms, where we say, okay, for all intents and purposes, h is going to be 0. So this is going to be practically 0. So what we'll get, a squared plus 0, or minus 1 over a squared. And that's going to be our derivative. Questions about that? Check the time. Okay. So let me do one more example. Well, let me ask this question. We'll do a part B. Let's say we want to find f prime of negative 1. Well, we already know what f prime of a is. So negative 1 over a squared. So in this case, we're just going to let a be negative 1. And so f prime of negative 1 will be negative 1 over negative 1 squared. And that's going to be negative 1. So questions about that? All right. So let's see. Let's do this one. F of t equals 16t squared. And this is the distance a falling object travels and falls near the surface of the Earth. So in this case, we're thinking of a distance that's positive, where we're falling down like this, and say you release something from, say, a tower. And as an object falls, after 1 second, it'll be here. After 2 seconds, it might have fallen here. So this is growing not linearly, but the distance falling, we're thinking of like a vertical fall is what we're thinking of. So what we want to do is find this. We want to find the instantaneous speed at t equals 1. We're going to talk about some physics, why we're calling this a speed. So let's keep in mind that speed, I'm going to be a little technical here. Well, I'm going to say velocity. Let's be careful here. Velocity is the change of distance, or delta distance, over delta time. Delta is change. So this is just sort of a math notation you'll see. You'll see this in physics as well. So delta means change. So change in distance over change in time. In speed is the absolute value of velocity. So velocity could be negative, but we're talking about speed in this case. We're talking about just how fast something is going. And we're not really concerned about the direction of it or anything like that. So we're just going to talk about absolute value of velocity. In this problem, this distance formula is always going to be positive. So for this problem, our velocity will equal our speed. So we're not going to have to worry about absolute value in this case. So, and the reason is our distance is always going to be getting bigger and bigger and bigger. So what we're going to look at here is how do we get a change in distance or a change in time? Well, f of t is equal to distance. So if we have f of t plus h minus f of t, that's going to be a change in distance. Now if we take t plus h minus t, well, that's a difference in time. We're changing time. But again, these are going to simplify down to just h. So h in this case will be delta time. So if we take the ratio of these two things, we're going to get a change in distance or a change in time. Now, in this case, we want time to be 1 second. So we release something, it's going to fall. So as we release it, what's the instantaneous speed at 1 second? So this will be the limit. As h goes to 0 of f of 1 plus h minus f of 1 over h. And again, this will be a change in distance. This is a change in time. So this is 16, 1 plus h squared. This is time, and that's time. 16 squared divided by h. So we'll FOIL that. This will be 1 plus 2h plus h squared minus 16 times 1. 1 squared is just 1. H. Limit of h going to 0. We'll distribute the 16 through here. 16 times 1 is 16. 2 times 16 is 32, and we have 16 h squared. And again, 16 times 1 is 16. So we're going to get some cancellation. Here and here. So hopefully we can get this to cancel out, and it's going to. We can factor out an h in the numerator. And once again, we can talk about dominant terms. And in this case, as h goes to 0, 16h is practically 0. So we're going to get 32 plus 0, or 32. Now this does have units. The function f, it measured distance in feet. And then this was divided by time, which is measured in seconds. So this is feet per second. And that's it. Questions about that? And I think that's a good stopping place. We've got 9 minutes left, but with 3.2 right around the corner, I think this is a good place to stop. It's a complicated section, and it'd be better if we just kind of do it in 1 unit. So that's going to be it. What we're going to do Wednesday, we'll talk about reviewing for the test. I'm going to print up some solutions for that practice test and get those out to you as soon as I can. Other than that, let me know if you have any questions. Again, we'll be testing on Chapter 2. And yeah, any questions about any of this, let me know. Other than that, I'll be having office hours starting at 4 o'clock. Other than that, have a wonderful afternoon.